Let me start by asking you a question, one that sounds like it should be impossible.
How in the world can you run a massive 20 gigabyte game, or maybe some huge video editing project, on a computer that you know for a fact only has 8 gigabytes of physical RAM? I mean, it just doesn't seem possible. How can you fit something that big into a space that's less than half its size? Well, the answer is this beautiful, almost magical trick that your operating system is playing every single second you use your computer. And it's truly one of the cornerstones of all of modern computing.
So today, we are going to pull back the curtain on this amazing illusion. We are going to deeply understand the concept of virtual memory. We'll see exactly how your computer performs this incredible feat and why it's so absolutely fundamental to everything you do. At its heart, the entire idea of virtual memory is built on an illusion. The wonderful illusion of having infinite, or at the very least a massive, private slice of memory for every single program running on your machine. You know, back in the early days of computing, things were a lot simpler, but they were also incredibly restrictive. For your program to run, every single part of it, the code, the data, the whole shebang, had to be physically loaded into the computer's RAM. So if your program was, say, 1 megabyte, you needed 1 megabyte of free RAM. If it was bigger than the RAM you had, well, tough luck, it just couldn't run. And this, as you can imagine, severely limited how big and complex software could get. And this is where virtual memory comes in and just completely shatters that limitation. It's a technique that brilliantly separates what a program thinks its memory looks like from the actual physical hardware. From your program's point of view, it sees this huge, private, continuous block of memory, its very own address space. It might think it has gigabytes, even terabytes of memory all to itself. But in reality, the operating system is in the background, cleverly mapping little pieces of that huge virtual space to the actual, limited physical RAM.
And this picture illustrates the idea perfectly. Over on the left, you can see the program's view, this massive, unbroken stretch of virtual memory. And on the right, you have the much smaller physical RAM. The OS, with a lot of help from the hardware, acts like a master translator, taking the virtual addresses the program uses and converting them into real physical addresses in RAM. Now here's the crucial part. Not all of the virtual memory needs to be in physical memory at the same time. Only the parts that are currently being used have to be there.
So that raises a pretty big question, right? How does the system decide which parts of the program to keep in RAM and when? Well, this brings us to the core mechanism that makes this whole thing work, the magic of demand paging. The key idea here is actually a form of really efficient laziness. Instead of loading an entire program into memory the second you double-click it, the OS just waits. It only loads a small piece of the program, we call that piece a page, from your hard drive into memory the very first time it's actually needed or demanded. Think about it like this. Instead of dragging your entire bookshelf to class, you only bring the specific chapter you need for today's lecture. This lazy way of doing things means your programs start up way faster and use a lot less RAM overall. So, what happens when a program needs a page that isn't currently in RAM? It triggers something called a page fault. Now, the word fault sounds like a bad thing, like an error, but it's actually a completely normal signal for the OS to jump in and do its job. First, the hardware detects that the memory location isn't available and it traps to the OS, which is just a fancy way of saying it pauses the program and hands control over. The OS then checks if the program is even allowed to access that memory. If everything's okay, it finds an empty slot, or frame, in RAM. Now comes the slow part. The OS tells the hard disk to go find the needed page and load it into that empty frame. Once it's loaded, the OS updates its master map, called the page table, to say, hey, this virtual page now lives at this physical address. Finally, it restarts the instruction that caused the fault in the first place, and your program continues running, totally oblivious to the complex dance that just happened behind the scenes.
And this whole demand paging mechanism enables a fantastic optimization called copy on write. Think about creating a new process. The old slow way was to physically duplicate every single page of the original process. As you can imagine, that takes a lot of time. With copy on write, the OS does something much smarter and lets the new process, the child, share all the pages with its parent. It's only when one of them tries to write to a shared page that the OS steps in, makes a private copy of just that one page, and updates the map. This makes creating new processes incredibly fast. Okay, so we've solved the problem of loading pages when we need them. But this creates a brand new problem, doesn't it? Eventually, physical memory is going to fill up. What happens then? We have to make a tough choice. So here's the situation. Our RAM is totally full, and our program needs a new page from the disk. To make room, we have to pick a victim, a page that's currently in memory, and evict it, kicking it out. The algorithm we use for this, the page replacement algorithm, has a massive impact on system performance. If you make a bad choice, you might immediately need the page you just kicked out, which causes another page fault, and everything slows right down.
The simplest strategy is called first in, first out, or FIFO. You just replace the page that's been sitting in memory the longest. It's really easy to implement, but think about it. The oldest page might actually be a really important one that's used all the time. FIFO also suffers from this bizarre, counterintuitive problem called Belady's anomaly. Get this, in some cases, giving a program more memory can actually cause it to have more page faults. It's totally backwards, but it happens because the new memory size can mess up the eviction order in just the wrong way.
So let's compare our options. The absolute perfect, optimal algorithm would be one that could look into the future and evict the page that won't be used for the longest period of time. The only problem is, well, we can't predict the future, so that's out. A much more practical and really effective approach is LRU, which stands for least recently used. It's based on a really solid assumption. If a page hasn't been used in a long time, it probably won't be needed again anytime soon. It's a great approximation of that perfect optimal algorithm, but implementing true LRU can be really hard on the hardware.
So, what do real systems do? They approximate LRU. A really common way is to use something called a reference bit. It's super simple. Every time a page is accessed, read from, or written to, the hardware automatically flips a little bit for that page from a 0 to a 1. Then the OS can periodically go through and look at these bits. A page with a bit that's still 0 hasn't been used recently, and that makes it a pretty good candidate to be replaced. This gives us most of the performance benefits of true LRU, without all the expensive hardware.
Now, managing all these pages is a really delicate balancing act. If the operating system starts making poor decisions about which pages to keep and which to evict, it can lead to this disastrous state where the entire system just grinds to a halt.
And this disaster has a name. It's called thrashing. You've probably experienced this. A process is thrashing if it's spending more time just swapping pages back and forth between RAM and the disk than it is actually executing useful code. To you, it feels like your computer has slowed to an absolute crawl. The hard drive light is blinking like crazy, but nothing is actually happening on screen. It gets stuck in this vicious cycle that happens when a process just doesn't have enough memory to hold all the pages it's actively trying to use at one time.
So, to prevent thrashing, we have to understand a fundamental truth about how programs behave. They show something called locality of reference. What this means is, a program doesn't just access memory randomly all over the place. It tends to work in one specific area for a while, then move to another area. This diagram shows that pattern perfectly. You can see these little clusters of activity, these localities, where the program is working intensely on a small set of pages before it moves on to the next task.
The way to stop thrashing is to use this knowledge. The working set model is a strategy where the OS actively tries to figure out the current locality of a process, what we call its working set. And the goal is simple. The OS makes sure that the process has enough physical RAM to hold its entire current working set. If it can't, if there's just not enough memory to go around, it might even suspend that process for a little while, just to prevent the whole system from getting dragged down into that thrashing chaos.
Now, these principles of virtual memory are so powerful that the OS uses them for a lot more than just running big programs. They actually enable some really clever, high-performance features under the hood.
One of the absolute best examples is memory-mapped files. Normally, when you want to read a file, it involves system calls and copying data between different buffers. It works, but it can be slow. With memory mapping, the OS does something brilliant. It maps the file on your disk directly into your program's virtual address space. Suddenly, the entire file looks like it's just a big array sitting in memory. When you try to access a part of that array, the OS uses demand paging to automatically load just that piece of the file from the disk. It is incredibly fast and efficient. And this same control over the memory layout is also a huge part of modern security, enabling things like address space layout randomization, which constantly shuffles where a program's parts are in memory to make it much harder for attackers to exploit it.
So, we've spent all this time talking about how the OS manages memory for all the programs you run. But what about the kernel itself? The operating system has its own memory needs, and they are very different and much stricter than regular applications.
See, the kernel is constantly allocating thousands of small identical objects, like process control blocks. Using a general-purpose memory allocator for this would be slow, and it would cause a problem called fragmentation, where memory gets broken up into all these tiny, unusable little holes. So instead, many modern kernels use something called slab allocation. They create these pre-made caches of objects, all initialized and ready to go, inside bigger contiguous blocks of memory called slabs. So when the kernel needs a new object, it just grabs one instantly from the cache. It's an extremely fast operation, and it completely avoids that fragmentation problem.
So let's bring this all the way back to our first question. How do you run that 20 gigabyte game on your 8 gigabyte machine? The answer is virtual memory. It is this intricate, invisible foundation that lets us run more programs than we actually have memory for, makes them start faster, and even gives us incredibly efficient ways to handle files. It truly is a beautiful dance between the hardware and the software, a partnership that turns the hard physical limits of our computers into the vast logical freedom that all our applications enjoy. And it makes you wonder, doesn't it? What other clever illusions are our computers creating for us right now?